that we are making an theorem.
Sorry, I'm going to interrupt. So, yeah. Just this is Dhananjay, like we're at MP Club. Firstly, thank you all for coming over here and sacrificing your Wednesday evening for a talk here at MP Club. We have with us today Professor Ravi Raghunathan from the Department of Mathematics, and he's agreed, thankfully agreed to us, like give a talk for a couple of hours or so on the topic of prime numbers and various other domains as well. So Professor Raghunathan has worked extensively on number theory and other domains of mathematics over his career, and we're very glad that he's agreed to share his valuable experience, some of it at least with us today. And yeah, thank you very much, sir, and I'd like to thank you.
So thank you for the invitation, Tejas and Dhananjay and the Maths Club in general. So okay, the number theorist is lucky because it's very easy to state the results from the theorem that you see. Right? If I was doing topology or algebraic geometry or analysis, you first have to have a whole bunch of definitions. You don't even know what the objects are, but everyone knows what number theory is because it's about the properties of whole numbers. Right? So that way we are extremely lucky when we go out to give a lecture of this type. It's quite easy to convince the audience that they're in a position to understand something. One is also, in some sense, in a less important sense, unlucky because it turns out invariably even the simplest problems in number theory are extremely hard to prove and usually require extremely deep techniques from other areas. Right? Whole numbers by themselves have only so much structure, and usually when you want to prove something about numbers, the only way you get at it is by understanding the structure of the whole set, but that's kind of hard to understand for integers, or at least integers with specific properties. Right? So anyway, let me begin at the beginning. So there are two theorems that Euclid stated in his Elements. And the first one, I put both in the abstract, right? So the first one, depending on what, let's say. I'm going to invert the order, I think, of. Let me keep the order, right? So every. And uniquely, every natural number can be written uniquely up to the order of prime factors, to the order of factors, to the order of factors. Whether I am being recorded, the order of factors as a product of prime. That's often called the fundamental theorem of arithmetic, and it was known to explicitly in this form already to the Greeks 2,300 or 400 years ago. Euclid wrote his books sometime around 330 BCE. So, and I'm sure it was known to people before that, probably to the other Greeks, probably to the Babylonians, probably to many other cultures. Maybe the Chinese, maybe the Indians, yeah. But we don't have a written record there. We have a very clear statement in Euclid's Elements, and this clarity we, I think, achieved only there, at least that many years ago. Okay, so that's. And the second one, also found in Euclid's Elements, is that there are infinitely many prime numbers. Of course, I have, slide versions of this talk in some form, but in general, I think it's better to do mathematics on the board. And invariably, when one has slides, one goes too fast, and the idea is, one ends up cramming a lot of information at the expense of understanding it. Okay, so there are two of these statements, and more or less, so modern number theory is sometimes divided into two branches: algebraic number theory, which uses the tools of algebra, and analytic number theory, which uses the tools of analysis or calculus, basically. Analysis is a glorified name for advanced calculus. Okay, so in other words, calculus with epsilons and deltas is called analysis. And all of you have seen an epsilon or a delta by this point, whether you like it or not in MA 105. First part of MA 105. Okay, so in more generally, the same Siddharth Gadgil who I was talking about a little earlier told me many years ago when he was a graduate student and I was just a little older, he said, I don't think it's his original observation, but the ends of mathematics, what do mathematicians want to do? They want to do either number theory or geometry. Yes. Right? And what are the means of mathematics? They are algebra or analysis. Right? So the means are algebra and analysis, maybe manipulating polynomials, algebraic identities, maybe studying rates of growth of functions, etc. But the ends of mathematics, usually what you want to do as a mathematician, you want to solve a problem in either geometry or number theory. And for example, maybe some of you are saying, but what about physics? Problems in physics come into mathematics are typically problems of geometry. Right? You do not solve a random partial differential equation. In fact, you can't as a rule. Okay? What you do is typically solve a problem, say, involving the Laplacian, most commonly, right? Wave equation, heat equation, Laplace of the equation, and invariably those equations, the solutions of such equations enjoy certain invariance under certain symmetries, right? So, for instance, the Laplacian has invariance under rotational symmetries, right? In general, for those of you who heard it, you have the orthogonal group, and that doesn't change anything about the solution of the Laplacian. So, it's only when there are some extra geometric features to the problem, right? Often that come naturally in, say, in the context of physics, that you can solve something like a partial differential equation. So I count that again as a problem in geometry when you solve such a thing. Right? So my view of geometry is quite broad. My view of number theory likewise will be broad. And so there are these two, major focus, major things one typically does as a mathematician, and there are two sets of tools: the algebraic tools and the analytic tools. And essentially, one can make a case that all of algebraic number theory is born out of trying to generalize the statement or refine the statement or make more variations on the first statement. Every natural number can be written uniquely, and that uniquely is kind of important as a product of prime numbers. But uniqueness is of course up to the order of the factors. We make no distinction between 2 times 3 and 3 times 2. We make no distinction between 2 times 2 times 3 times 2 and 3 times 2 times 2 times 2. Right? So that of course we consider the same. Okay. The second statement, I can argue, gives rise to analytic number theory. Right? When you see the word infinite or infinitely, that's suggestive of analysis or calculus, and that's how you get trying to make more and more precise statements and related statements to theorem 2 gives you, in some sense, you can argue that all of modern analytic number theory descends in some way from this statement. So obviously, it's an exaggerated claim, but I'll try to give some evidence in its favor. And of course, none of these statements should be taken literally, and they're obviously only morally true, they're not literally true. But roughly, I think there's a reasonable philosophy base. And of course, I should emphasize, of course, that there's a tremendous interplay between algebraic and analytic number theory. That's been one of the features of the last 150 years or so. So, because of the way things are, in some sense, and because you have more exposure to calculus, I think it'll be a little easier for me to actually start with theorem 2 and maybe say something, give a kind of distorted history of some problems with analytic number theory. First, and if we have the time and the enthusiasm and the interest, we can perhaps say something about the first theorem and algebraic number theory. That's a little harder to do without knowing more algebra. It's a little harder to say sensible things about problems in algebraic number theory, but we can make something. Okay. So good. So let's start with theorem 2. So there are some obvious questions that beg to be asked. So when you say there are infinitely many primes, the first question is how infinite? So infinitely many just says there are large numbers of them. No matter how many primes you have, you can always find another, right? But you've all seen now, already 11th and 12th standard, functions like exponential of x or polynomials of x and so on. So we can ask a more refined question, how infinite, what do I mean? I take a real number x I count all prime numbers, positive real number of course. I take all prime numbers that are less than x, and I can call that function phi. So let's start. So this is sometimes called the prime counting function, and it is the cardinality of the set p prime such that p is less than or less than or equal to x. It's a matter of taste whether you say less than or less than or equal to. It makes no difference or whatever. Right? At most it can differ by 1. If x happens to be a prime, you would have counted 1 more. Yeah. So, okay. And now you can ask, so what the prime theorem 2 says what? Says as x goes to infinity, pi x goes to infinity. So what does theorem 2 say? Restatement of theorem 2 says limit as x goes to infinity of pi x. This is just the restatement of theorem. Right. Okay. Right. And now, as I said, the obvious question to ask is, there are so many different functions that go to infinity. So of course, pi of x is obviously less than or equal to x. It can't possibly exceed x. But you can ask, does it grow like x to the half, or something in the floor, x to the 1 over 17, right? That's where it goes to infinity. Does it grow like log x perhaps, which goes to infinity slower than any power of x, but maybe it's like that. Okay? So you can ask, how infinite? What is this function pi? That's a natural question to ask. Right? And indeed, of course, mathematicians asked it. So let me, so how fast? So how fast does pi x grow as so of course the structure of the talk will be, I will try to keep the first year students with me for, let's see, at least 20 minutes to half an hour, and then I don't guarantee anything. Yeah. Of course, it doesn't mean the other people will follow either after half an hour. It's more or less guaranteed. And of course, by the way, stop me if you have any questions. Very often in mathematics, one fails to follow just because one doesn't know a single word. One definition you don't know, and then you have no idea what the next is talking about. So if you don't know a definition, stop and ask. The worst I can say is, I can't tell you now, you have to ask me after the lecture. So, when in doubt, ask the question, and very likely it's somebody else's question also. Get it solved for many people. Okay, so how does one attack such a question, right? So as I said, okay, we have, we're just going to sit there looking at primes. All of you must have had this feeling already if you've ever thought about prime numbers or whole numbers. There's just not much, it's hard to get your a handle on what. Okay, so, alright. So let's remember, there are two proofs that one typically learns of. Most of you would have learned one in high school. Why are there infinitely many prime numbers? Well, the NCERT book gives the usual proof that Euclid gave, which is, well, suppose there are only finitely many prime numbers. Well, let's call them P1, P2, etc. to Pn. Let's say, suppose there are only n. But now you take the product of all these prime numbers and add 1. And the point is, when you have the product of all these prime numbers and you add 1, none of the existing prime numbers can possibly divide. So either this number is a new prime, right, or some prime other than these must divide it. Because if it's not a prime, it factors, and you can keep factoring until you get to some prime. And so therefore you get a new prime contradiction. Right? So either the number P1, P2, Pn plus product of the Pi's plus 1 is the prime itself, or it factors into primes again, that we know, that's easy. By induction you can see every number can be written as a product of primes. Uniquely is a little harder, but just the product of primes is easy. And so because you know it factors as a product of primes and none of the existing primes divide this new number, there has to be another one, which was not on your list, and that's a contradiction because you assume that you had already listed all the possible prime numbers. So that's a proof, but that unfortunately gives no clue as to how to answer the second question. So this question is fed to Euler. So famously Euler gave the Euler's. I'm going to give a slightly souped up version of Euler's proof. I got some notes just in case I forget. we are now going to assume that we know theorem 1, okay, that's a given. And so Euler said, let me look at this number. This is the zeta function, right? So square. Well, we call it the zeta function of V1, although of course Euler is the one who introduced the function, but zeta was introduced by V1, and this is part of the general Arnold principle in mathematics, which is if something is named after someone, then that someone did not discover it. And then the question is, does the Arnold principle apply to the Arnold principle? And indeed it does. Arnold was not the first to speak it. Okay, so you have the zeta function, and it's defined as a series sometimes. So right now S is a real number. Yeah. In the not too distant future, in about 20 minutes, it will become a complex number. Right. So zeta S is defined as a series summation n equals 1 to infinity, and all of you know, of course, from 11th standard, 12th standard, whatever, that this series makes sense. Well, I've written real S, but it's a real number, so that's logical. Where is the? Do we have an eraser? That's the. Right, so it makes sense. Perfect sense. Okay, so it converges, and in fact, with a little bit of analysis, which you typically don't see anymore in IIT, but you used to see when I first joined, because there used to be second year courses, including compulsory for everybody. There used to be 3 maths courses. There was something called MA 203, which dealt with convergence of series, and in particular, you see, this actually defines a function for each S. It's defined by a series. So this actually, if you think about it, this is a series of functions. And you're asking, you can ask, is this a continuous function, for example, in the variable S? And in fact it is. It's not very hard to prove. Yeah? There's something called the Weierstrass M test, which allows you to, for those of you who heard it, but the words which allows you to conclude that this is in fact, this output is continuous in S. It's even better. It is in fact differentiable, it is infinitely differentiable. You can take as many derivatives as you want, and you can take it in exactly the way you think you can take it, maybe you can differentiate term by term. Even better, it's what we call an analytic function. You can expand this thing in power series as a function of S. Okay? So it's as good as you can get. I usually emphasize in my beginning calculus class that, of course, analytic functions, that is functions given by power series can always be differentiated term by term. Okay, there's no issue. Take a power series, it converges. You differentiate term by term, that's a new series that will again converge. Not an issue. And in fact, the differentiated series will be the derivative of the original series. So basically, power series function like polynomials, you can just differentiate without thinking about it, just differentiate term by term, no problem. Okay? So that's the sort of series this is, and just to remind you, being a power series is much stronger than just being infinitely differentiable. All power series are infinitely differentiable, but just because a function is infinitely differentiable doesn't mean that you can write it as a power series. Sometimes the Taylor series does not converge to the function. Yeah. Reminder to those who took my course, e to the minus 1 over x when x is greater than 0, and 0 when x is less than or equal to 0. So that's an example of a function. It's infinitely differentiable, so you can write a Taylor series down. The Taylor series will converge, makes sense, but it will not converge to the function. It will always give you the value 0. Whereas the function is e to the minus 1 over x when you have it. So yes. So anyway, this is what we call an analytic function that is given by power series. In any segment, you can make an expansion and it will give you a power. Such a function is called analytic. In passing. Okay. So what does this have to do with number theory? Well, here's what it has to do with number theory. You see, we have another formula for zeta S. In V, you can write it as the product over the prime numbers of the the function 1 over 1 minus 1 over p to the s. And that, how do you see that these two, this again is valid for real s greater than 1. How do you see that? Well, this is, of course, should remind you of the formula for geometric series. This is your 1 over 1 minus r. When you expand out, what does any one factor look like? Well, 1 minus 1 over p to the s. Inverse looks like 1 over p to the 1. 1 plus 1 over p to the s plus 1 over p to the 2s and so on, right? Now you take all of these factors across all primes and you open out the brackets. What do you get? You get all possible products of different prime powers. And by the theorem on unique factorization, that's exactly all integers. So when you take this out, it turns out that this thing is nothing but that. So this thing is called the Euler product. This is what, when you write down a series, what has it got to do with primes? Nothing a priori. But once you see a product, you begin to appreciate that it might have something to do with prime numbers. Right? Might control prime numbers in some way, and it does. Okay, so this is called the Euler product. This, in fact, does not satisfy the Arnold principle. Euler indeed was the first person to discover the Euler product. Okay. Another duster. Okay, so this is just motivation. So erase it. Okay, so far so good, I assume. I assume I've carried most of my audience. So now let's. So what is the Euler's proof? I'll give you the rough proof, then I'll give you a slightly better version. Yeah. So suppose the number of primes was finite, right? Then this product here is just some finite product for any value of s. So there's no convergence issue at all. It's just finite stuff, right? So for any value of s greater than 1, it converges, makes perfect sense. And in fact, as you let s go to 1 in the limit, it also makes sense. 1 over 1 minus 1 over p. Right? This is a finite product, there are only finitely many primes, it makes sense. On the other hand, obviously, if you use this one and let s go to 1, then you know that summation 1 over n is infinite. So Euler gives you a second proof of the fact that the number of primes. So what do we take away? Knowing one small fact about the zeta function, namely, so if you know the simple fact, limit as s goes to 1 plus, that is you come from the positive reals of zeta s. If you know this is infinity, then you know the number of primes is infinite. Right? So knowing one thing about the zeta function, and from the Euler product you could read out one more thing, which is, notice something, when you have a product like this, you can easily check that the function zeta s never vanishes when s is bigger than 1. Yeah, it's a product. In order for a product to vanish, so you can always take log, then it becomes a sum, and you can easily check that log, but sum converges to something perfectly reasonable. And then what you started with is the exponential of the sum. An exponential of something is never 0. Right? So that's it. So another thing you read off easily from the Euler product. So this of course implies theorem 2, is what I was trying to say. But the other thing is, notice fact, remark, whatever. Zeta s is never 0. So moral of the story, if you know something about the zeta function, it looks like you know something about primes, even just at one point. So perhaps you can do much better as we learn more about the zeta function. Alright. So how does this, so how big should pi of x be? I had someone now. So let me do this slightly more precisely while I'm at it. And since so I've already given one proof, so I satisfy the general dictum that every mathematics talk should have at least one proof. That much I've done. But let me just, since it's a simple enough calculation and it's calculus, I think it's worth just noting this thing down, right? So I'll do slightly better than the statement that limit as s goes to 1 plus, I'll even tell you again how it goes to infinity. So my point is, it will look like 1 over s minus 1. The function zeta s near 1 looks like 1 over s minus 1. Okay? So that's an even more precise statement, right? It's not just goes to infinity, goes to infinity like 1 over s minus 1 goes to infinity as s goes to 1. Yeah. Okay. Yeah.
Might be getting a little late. Are we deriving that from the polylogarithm series?
Are we deriving it from the what?
Like s tends to 1 plus 3s is equal to 1 by s minus 1.
I'm about to do it. It's very simple.
Okay. So, okay,
It's a one variable calculus thing. Yeah. It's very simple, of course, it doesn't prevent me from forgetting some small detail on this. That's why I make sure I carry this thing.
Sure.
You don't want to make a mess in a talk like this and then, spend 15 minutes figuring out you got some minus sign wrong or something. So that you should not do. Okay, so here it is, right? So we can do a little better. So look at this function t to the minus s. S is of course a number bigger than 1. It's a monotonically decreasing sequence, right? So look at it. So because it's monotonically decreasing, right? Function in t greater than or equal to 0, and let's say s, let's look at s greater than 0. So this of course is a monotonically decreasing function, which means of course that 1 over n plus 1 to the s is definitely less than integral n to n plus 1 of t to the minus s dt, and that in turn should be less than 1 over n. Does that work? This is a monotonically decreasing function, and I just took the endpoints. So obviously, if I took the constant 1 here, etc., that would do it. So once you have this, you realize, right? If you sum over all n, what will you get? You get zeta s minus 1. Just sum over all n, you're missing the first term, right? On the other hand, what is the integral? When you sum over all n here, you just get the integral from 1 to infinity, right? So you just get less than integral 1 to infinity of t to the minus s dt, and obviously less than zeta s. Okay. So which of course allows you to say that 1 after you. So of course, what is this? This is nothing but 1 over s minus 1, right? So here. So this of course equals 1 over s minus 1. This in turn is of course less than zeta s. Now you can multiply throughout by s minus 1, if you like. And what happens? If you do that, you get zeta s, s minus 1 times zeta s, right? On the other hand, what do you have to do? And then of course, if I put multiply throughout by 1, I have s minus 1 times zeta s, that's bigger than whatever was there, right? So this should be less than, what I end up getting 1 is less than, after dividing suitably, you get 1 is less than s minus 1 times zeta s times less than s. You can easily get that this is what you are getting. Okay? Or less than, right? So small amount of work, take the s minus 1 up here, you get s minus 1 times zeta s, go through the motions, and this is what you get. Okay, so this is good news. So first of all, this tells you that zeta s is bigger than 1 over s minus 1 for sure. So it's definitely going to infinity faster than that. Okay, and on the other hand, zeta s is also less than s by s minus 1, and as s goes to 1 again, it looks like 1 over s minus 1. So either way, it looks like that. If you take limits, yeah, so take limits. As s goes to 1, will tell you what? Will tell you that 1 is less than s minus 1 times zeta s. And from this, you see that zeta s exactly is in the limit nothing but 1 over s minus 1. So the way we write that often is zeta s looks like 1 over s minus 1. This means exactly that as limit as s goes to 1, zeta s divided by s minus 1 is going to be 1. So they have, this says that you take the product s minus 1 times zeta s goes to 1. That's the meaning of the statement. When I put this little tilde, it means that they grow at the same rate, exactly the same. Okay, so and if you take log, you see you get log zeta s looks like log 1 over s minus 1. So and of course, so log zeta s looks like log 1 over s minus 1. That's what it is. Yeah. So as you can see, no polylogarithm and all that.
Nothing is required.
Utterly clear. Yeah.
Just sandwich theorem.
Sorry.
Just sandwich theorem. Nothing else.
Yeah.
Yeah.
Yes. And you have to know how to integrate e to the minus.
Yeah.
Yeah. So many of these things are often much simpler than the proofs given. There are, of course, I've gone out of my way in this particular talk to pick the simplest proofs that I know, so that it's as accessible as possible. Okay. All right. So if you want to give a slightly more rigorous proof, rather than saying summation 1 over n diverges and etc., because I never really did many things, but from this it's clear that zeta s behaves like 1 over s minus 1 and therefore really does go to infinity. Okay, so from this hand wavy argument saying let s go to 1, yeah, it's true, of course it does diverge, but we never proved this was a continuous function etc. of s. We never did it. But here we are really getting for free all of many of those things. Just to point out, there's nothing wrong with the argument I gave first. It can be made perfectly rigorous. In fact, if you like, this is one way of thinking rigorous, and it's a perfectly good way to think. But if you want to be extra picky, you do this. Okay, so this is what I wanted to say about the zeta function. So as I said, this is Euler's proof of the fact that there are infinitely many primes, and it's the start of all analytic number theory. Yeah, although that honor is usually bestowed on another theorem due to Dirichlet, which I will state shortly. So okay, so what is this is good news, but what is we have still not really answered the second question I asked, which is how infinite. Okay. So all I've done is tell you quite precisely how zeta s behaves near 1. Looks like 1 over s minus 1. In particular, that means that if you subtract 1 over s minus 1 from zeta s, right, in some sense all the infinite stuff will go away, and that limit will be finite as s goes to 1. That is, take zeta s minus 1 over s minus 1 and take limit as s goes to 1, you will get a finite number. Okay. You can make much stronger statements if you know complex analysis, but for those who have seen these words, it's saying that zeta s has a simple pole at s equals 1 with residue 1.
Yeah.
Okay. And that statement has no more meaning than this statement, which is the more fancy way of saying it. So, okay. Fine. This limit is fine. Okay. Right. It's a good thing to know. So once you subtract off that polar term 1 over s minus 1, that's where all the bad stuff is happening. Zeta s minus that behaves extremely well. And yeah, all right. So let's do some historic stuff, right? So after Euler, many people began to suspect that the zeta function, we should really look at the zeta function more closely. And of course, the one mathematician who suspected everything and knew everything was Gauss. But before Gauss, there was Lejeune. So the question is, how big should pi x be? Right? What is the size of pi x? And Lejeune suggested in a letter to MK, I think, that his conjecture was that pi x is x by a plus b log x. This function for some constant c n. So his relation, log x goes to infinity much slower than x. In fact, much slower than any power of x. So really x by log x grows faster than x to the 1 minus theta for any positive theta. So it doesn't grow as fast as x obviously because you have divided out by this much, but faster than any power less than 1. Okay. So this was Lejeune's guess, and as in all things, Gauss came up with the correct answer. He said no, a should be 0 and b should be 1, and in fact he did a little better. So Gauss said pi x not equal 30. So what does this mean? This means take pi x and divide by this expression, the limit should go to 1. That's what it means. Okay? So here Gauss said, look, no, there should be Lix. By the way, a small note, when mathematicians say log, we only mean log to the base. Yeah. There's no ln business. Log is always log to the base. It's an unfortunate fact that we don't have e number of fingers and toes, but we have 10. So we probably should do it that way. But e is obviously the more natural thing to take. Okay. So if you do pi x, what is Lix? Right? Lix is integral 2 to infinity. Yeah, if you want to take 2 because you have a log there. So this is what Gauss said, that phi of x looks like this function. Oh. So you have this function and this is the correct one, and moreover if you do integration by parts, you will realize that this actually looks like x by log x minus x by log x and a power of x, then in fact there's some other term 2x plus log x cube dot dot dot. Okay. So the prime number theorem, this is the most precise form of the prime number theorem. This is what we call the prime number theorem. The conjecture by Gauss, and this it was then proved a little later. This term is called the, so what we have is, so sometimes equivalent form prime number theorem is also stated as phi x is asymptotically equal to x by log x. Why? Because that's the first term without these correction terms, but this is the more precise form. This is the one form that has been proved. So the number of primes less than x grows roughly like x by log x, but more precisely like the function Lix. And now realize people at this end can probably barely see that board, so you probably restrict myself to smaller part. And you could move the board a little bit. Yes, good idea. Yeah, maybe when working on it, but then again the point is lost because you're supposed to see the previous board. But okay. Yeah. So this is the prime number theorem. And of course Gauss was right in his conjecture. And in about 1896, this theorem was funded.
So he just gave that without giving any proof.
He couldn't prove it. It's a conjecture, right? When we can't do something, we say, okay, it's my guess.
From where did he bring that?
He's Gauss. He knows everything. No, he actually did give a heuristic. He gave reasons for why this works. And in fact, let me make a plug for a book that I always like. There's a book called What is Mathematics by Courant and Robbins. And in that book you will find Gauss's heuristic proof. I don't know Gauss, but you'll find a heuristic proof, and I think it was due to Gauss. So this is excellent. It was written almost 100 years ago now. Not quite, 1930 something maybe, not quite 100. Right? And this is by Richard Courant and Robbins. Robbins is, yeah, something wrong with Robbins.
Yes, sir, Robin.
Probably only 1 week. Something. There's something, maybe 2 weeks. I don't know. Anyway, so then you will find a thing. First of all, people do numerical experiments. People in the 19th century used to do horrendous computations by hand. And Gauss probably calculated very likely, let's say the first 1,000, 10,000, whatever primes or something like that, and actually observed and then calculated x by log x and then matched the value. They did things like that. They were absolutely fearless calculators, and often, Gauss spent 20 years of his life calculating the orbit of one asteroid called Ceres. Yeah. And the mathematics he did was in the time that was left over from those 20 years. Yeah. So, and from, of course, Gauss's law in electrostatics and things like that. Yeah. So there was a lot of misspent time.
In statistics as well, Gaussian
Sorry?
process. Gaussian process.
That's the name we give now. Of course, he studied the function e to the minus x square, and it looks like that. So we call it, when things are distributed that way, we call it a Gaussian distribution. But to my knowledge, he didn't really pursue probability so in any very concrete way. Although I think there are some things he did you can, yeah. So even the prime number theorem, there are some probabilistic arguments there. But the general rule of thumb is Gauss pretty much knew everything, and you couldn't. It was unfortunately literally true, right? So many young mathematicians, Gauss was maybe 50 or something, and many young mathematicians go to Gauss and say, "Oh, I've done this." And And then Gauss would pull out some old notebook from 25 years ago and show them that, he'd done it long ago. Gauss didn't like to publish stuff. He rarely published his results. So his motto was few but right. So unless he thought, he had everything complete and the theory was completely satisfactory, Gauss would not. And of course, in those days, anyway, it's not just the internet. It was often ideas and papers would take years to move from just one country to a neighboring country and so on, different languages and so on. So, somebody may do something in 1820, but you may not become aware of it in 1830, if ever. I mean, sometimes things just got lost. And in any event, so Gauss had these notebooks. It apparently had so many ideas between 17 and 21, the ages of 17 and 21, that he found it difficult to record everything. But anyway, he wrote a lot of stuff down, kept his notebooks. And every time some young guy came and said, I did something, he said, yes, I did. Disappointed. So anyway, so Gauss has this idea, and what does he? This is good. And people began to suspect that if you knew a little more about the zeta function, then somehow maybe you could prove this. And I'm going to fast forward. There are several people, including Eisenstein and Mertens, who studied the zeta function. But we'll go straight to Riemann, who in 1859 wrote a series of papers on the zeta function. So actually, he had been working on it probably for maybe Eisenstein, who died very young, in 29, around 1859. Right. What I'm going to say. By the way, the pantheon in mathematics, right? The three great guys is supposed to be. Let's see, we take a poll. So this is something I tell my students. That if I ever ask you on a quiz or an exam who the three greatest mathematicians are of all time, then there's only one answer. This is the only thing in particular about. You should be able to say, and otherwise you get 0 on that particular question. So anyway, I'd like to poll the audience. So who are the three greatest mathematicians of all time?
Euler, Gauss.
Euler?
Gauss.
Euclid?
Euclid? No, we don't count Euclid because he was a textbook writer, is what we believe.
Okay.
So it's as though you took Stewart. See, that's what has survived. It's possible, we don't know. But most likely, these were discoveries made by other people, and Euclid was writing a textbook, mathematics textbook for maybe school students or whatever. There were no real colleges, etc. Whatever it is for students, right? So this is why we don't consider Euclid a great man. However, if he's proved even like 1% of what appears in his book, of course he's one of the greatest mathematicians of all time. But no, Euler no.
Archimedes.
Very good. Archimedes, then
Newton?
I heard the second name. Newton, of course, and Gauss. Yeah, so Archimedes, this is the Holy Trinity, typically for mathematicians, Archimedes, Newton, Gauss. But for Gauss, the Trinity was Archimedes, Newton, and Eisenstein. So he thought very highly of Eisenstein, who happened to die at the age of 29. And so he had these three people together as great. Anyway, so what happened in 1859 was Riemann rediscovered the zeta function that Euler had introduced. But he did something extra which other people had also done. He said, let S be a complex number. Yeah. And if you think about it for 2 minutes, S is of course sigma plus IT, real plus imaginary part, right? And I can write it like that. And some thought will convince you that you can make perfect sense of this series also. Who says you can't sum up complex? You could sum up real numbers, you can sum up complex numbers as well. Just sum up their real and imaginary parts separately, whatever. Do it. Okay. So this makes perfect sense whenever if real S, which is sigma, real part of S, which is sigma, is greater than 1. So this converges very nicely. So now we have the complex plane. We have real S equals 0 here. This line, the x-axis, the y-axis, and we have this real S equals 1, this line here. And over here, the zeta function makes perfect sense. So in fact, by the way, it's also clear that you see this is in absolute value. Let me do it like this. 2 minutes of thought will convince you that this is less than or equal to summation You can obviously take the absolute value inside, just like you do for real numbers, triangle inequality is all good. And here, absolute value of 1 over n to the s is actually just 1 over n to the sigma. Because n to the it has absolute value 1. Right? What do I mean by n to the s or n to the it? We mean e to the it log n. That's what it means, but anyway, let's not dwell on that too much. So this is nothing but 1 over n to the sigma. And therefore, if this makes sense, this is going to make sense. Yeah? Again, if you want, you can say Weierstrass and test or something like that. But you know, that's what it is. So now, and again, as before, you will find that this function now, you know, one can talk about power series with values in complex numbers as well. So this actually has an expansion in power series as well. So it will look like summation a n s to the n around 0 for it, not around 0, but if we take any, we are not near 0, but if I take any point here and call it alpha, I can expand this function around that neighborhood and I can write it as a power series. Summation a n s minus alpha to the n. Yeah, so this is once again what we call an analytic function. So in this entire region, it's a very nice function. It makes perfect sense. And further, just like before, we can actually check that it does not vanish. So again, zeta s is never 0 if, for the same reason as before, you can take, it's a product, you can take log of it, that log will converge, and then what you have is an exponential of it. Yes. Good. First question. For serious question.
Makes sense for real part greater than 1, but how do we say that it won't make sense for real part less than 1? Like it would diverge.
I didn't say that it won't make sense for real part less than 1.
But
But certainly at s equals 1, you know it's infinite, no?
Yeah, but for like real part less than 1 and there is some imaginary part, would there be any values where it would
Yeah, indeed. So we're coming to that point. So that is the whole point. So what people realize is, what you see in this, so here's a function. This is a function of a complex variable. So you should think of zeta as a function from complex numbers to complex numbers now, or at least from this part of the complex numbers to complex numbers, right? So actually, see, it's a half plane. Should be greater than 1. So as long as you're to the right of this line, everything is fine. Yeah? Okay. So now, but here is a remarkable thing. You can actually make sense of the zeta function even when real s is less than 1. And in fact, zeta s minus 1 over s minus 1 is going to make perfect sense. Okay? So the one point that gave trouble was 1, where you know it's infinite, but if you subtract off the 1 over s minus 1, then you know that it makes perfect sense. So in the language of complex analysis, zeta s minus 1 over s minus 1 is what we call an entire function. It's a perfectly well behaved function. It has power series expansion everywhere. It's beautifully behaved. It has all possible derivatives, etc. It's a very well behaved function. However, I'm kind of putting the cart before the horse because the only definition we have makes sense only for real is greater than 1. So what we really do is we give some other formula here, another definition, which coincides with this one when real s is greater than 1, but which also makes sense when real s is less than 1. So this is sometimes something you often do in physics actually. There are some number of EC students, right? You will often, this is what you call getting an analytic continuation. And later on when you do more fancy stuff like quantum field theory and so on, and you study spin particles, spin systems, this often plays a role. Yeah? So what will happen is you have a function that's defined by some formula. That formula makes some sense somewhere. But it turns out sometimes there's a diff, and that's good. I mean, a series is good, you can often understand what's happening. But there may be some other formula that may not be as good to understand the function here, but that formula will make sense in a larger domain. Yeah? And then there is something called the principle of analytic continuation, saying that if there is a formula for which zeta, which allows you to make sense of zeta in a larger domain, there is only one such formula. It's unique. It's not like you can extend this in two different ways. Right? So if I have a function that coincides with this series in the right half plane, there is one, but is also say defined here. Let's say there is only one way to do that. So this is called the uniqueness of analytic continuation. The principle of analytic continuation says if it is possible to find another formula which matches this one where you already know it, then that is the only way to do it. You might give a different formula, but the value of the function is going to be the same, no matter what. Yeah, so that's an important point for me. There's a small calculation that I can make. First, let me just make sense of zeta. Again, it's a it's much easier than it looks, and typically you don't see this proof. This proof I learned there was an Indian analytic number theorist called Ramachandra, and I think he's the one who came up with this proof. I guess about 50 or 60 years ago. He died about 10 years ago, but he was a well-known Indian number theorist, perhaps one of the best known, and he spent most of his life studying the Riemann zeta function. Okay, so let's. So what I'm going to tell you is there'll be some leap of faith here, yeah. But let's go. The actual calculation is just calculus calculation. Okay. So what happens here? So I say 1 over s minus 1. As you know, we've already seen is nothing but integral 1 to infinity e to the minus s dt, right? And that we have agreed the summation n equals 1. This part we saw before. Integral now a slight variation on the theme. 1 over, so t to the s is of course 1 over t to the s, right? So maybe a little bit like that. But now I'm going to be going from 1 to 2, 2 to 3, etc. And then I'm going to change a variable, so it's going to be this. Let's put let's say let's put the variable t1. Doesn't matter what you call the variable, right? I change the variable from t to t1. But this is true. Stay a little bit and you can easily convert. You just make a change of variables. N plus t1 equals whatever u or something. Then it automatically go from n to n plus 1, and you'll just be summing the integral from n to n plus 1 of this. Not, trust me, it works. Okay. So this we do this, and so we look at zeta s minus 1 over s minus 1. That is just going to be, well, zeta s is what? Summation 1 over n to the s. But 1 over n to the s is integral 0 to 1 dt by n to the s. It's just a constant. It doesn't see the t anywhere, right? So I'm just going to point out that this is nothing but summation n equals 1 to infinity, integral 0 to 1, 1 over n to the s. Just put the 1 over n to the s into the integral. Makes no difference because the total mass is 1. And then here you have 1 by n plus dt. Or t1, right? Which is going to be equal to summation n equals 1 to infinity, right? Integral 0 to 1, and then take a common denominator, so to speak. We do the fraction, and this is by n to the s by n plus t 1 to the s. Yeah. Now what have we gained here? Here's what we've gained. You can do this more carefully, and I've done it, but it's better just to, I think, give a quick idea. This thing here looks basically like n to the 2s. N to the s here and n to the 2s there. Right? So n to the 2s is there. Okay. Here, the leading term is n to the s, but when I make a binomial expansion, the first n to the s will cancel here. So I'll only be left with n to the s minus 1. So this thing will actually converge not just for real s greater than 1, but for real s greater than 0. Yeah? Because there's a difference. So you're saying nothing more than 1 over n minus 1 over n plus 1 looks like 1 over n square. You see this many times. The n plus 1 and the n minus n cancel, and then you just get a 1 on top, and so that's what's happening. Yeah? So this thing here makes sense for real s greater than 0. Not just 1. So you've succeeded, you've moved from here to here. You just subtracted the 1 over s minus 1. 1 over s minus 1 makes sense whenever s is not equal to 1. And the rest of it, this form. So now you've got a different formula. You see, it's not the same old formula for the zeta function. So you say zeta s is equal to 1 over s minus 1 plus some integral and some sum. But that integral and sum makes sense in a larger domain. So you move from here, so it suddenly starts making sense here. All but, and anyway, since I've subtracted the 1 over s minus 1, I don't even have to bother about whether it became infinite or not. It's not infinite, it's a perfectly good function. And a little bit of maybe thought will convince you that actually you can keep going. You went from 1 to 0, but you can go from 0 to 1 minus 1 by doing one more integration and splitting this difference. Okay? I don't want to do it now, it just makes life complicated unnecessarily. But what you can therefore do, by doing this process inductively, you can actually make sense of zeta of s minus 1 over s minus 1 in the whole complex plane. And it will in fact be given by power series, etc.
With this student, I'm just curious to
Sorry?
I'm just curious to know how this same process will be working to extend to s minus 1 at close to this one.
S minus 1.
Open domain of minus 1 to 0, open domain of minus
No,
1.
this makes sense for here as there is 0. That much
Yeah.
Okay, so you have to do one more differentiation here. I mean, you introduce another variable, you take n plus t1 plus t2. See, each, what did I do here? Okay, I'm only going to spend 30 seconds on this and then I'll move on after the thing. But what did I do here? I wrote, I introduced this 1 over n to the s and I put a 1 over n plus t1 to the s, right? But I can write this as 1 over n plus t1 plus t2 to the s and do one more integration.
Yeah.
And then you can add and subtract and you can do the same. It's a pretty clever trick. But you can keep going and you can go all the way to infinity. So at least to make a precise statement, after doing all this, what we see is repeat. Repeat, rinse and repeat as they say, keep doing it, push it all the way, and the upshot is zeta s by 1 minus s minus 1 is what we call an entire function. For those of you who have seen complex analysis, for those of you who have not, the short version is, look, this function is given by power series in any neighborhood value. So it's very well behaved function. And this is a proof. Yeah. So if you, the only reason you don't know, you know the proof, but you don't know what the theorem says exactly if you don't know what complex analysis is. But, so here's an example, right? When s is real, all of this makes sense. And we are just saying that zeta s by 1 minus s minus 1 is a nice infinitely differentiable function which can be expanded in power series. Its Taylor series is nice and it converges to this function. So it's a good function. It's very well behaved. And that's it. But now, the good news is you see you have made sense of zeta function even here. The zeta function itself will make sense on this line except maybe at this point. In fact, except at this point where it blows up. Zeta s minus 1 over s minus 1 makes sense everywhere. Zeta s by itself makes sense everywhere except for this point. Where it behaves like 1 over s minus 1 in neighborhood. Again, the complex analysis language, it has a simple code of order 1 with a residue 1 at s equals 1. Never mind. The hope is I say these words and then one day you will learn these words for a year in some textbook and you remember, okay, I saw this once and it's template. Beyond that, one is not trying to do. So, zeta s now makes sense everywhere in the complex plane, and so now it turns out, and this was Riemann. So Riemann did give this proof, he gave another proof using what's called the Poisson summation formula. Some of you may have seen this. Summation f of n is equal to summation f hat n. When formulas are nice, f hat being the Fourier transform. No?
Yes.
Somewhere it came. We're dealing with the heat equation surely. If you've seen the heat kernel, then you use this. Okay. How many of you have seen the heat equation or the heat kernel? Show of hands. You know there's something called the heat kernel and behavior at t and 1 over t is similar, right? As theta of t looks like square root of t times theta 1 over t. Have you seen this fact? Perhaps not? Okay. So general fact, if f is a nice function which decays rapidly, summation f of n summed over the integers is equal to summation f hat n. That's called the Poisson summation formula. Riemann used that formula to derive many things about the zeta function. So I'm going to take 5 or 7 minutes more and then I'll call it the end of my lecture and we can continue if people have further interest. So, okay. So what do we know? So now we have this zeta function, in particular zeta 1 plus it, and Riemann hypothesis, right? So this is the famous, perhaps the most important unsolved problem in mathematics today, whatever that means, right? So now you made sense of the function everywhere, and Riemann says, look, so we already know zeta has no zeros here, right? It never vanishes here. But Riemann says I can go all the way up to half. In fact, all the way up to. So Riemann hypothesis says f lies between the line 0 and 1, then in fact, okay, I'll tell you why this. So in this is called the critical step. So this is between 0 and 1. And Riemann says, look, the Euler product anyway told me it's not here. But Riemann says I can go all the way here. Okay, in fact, it has, but let's put and Riemann realized that this fact, this by the way you get $1 million if you prove. There are these Millennium Prize problems given by the Clay Math Foundation. There were 7 of them, but one got solved quite soon. The Poincare conjecture got solved in 2005 by Gregory Perelman. No, 2003 by Perelman. 60 got the fees. Yeah. So that one began, but there are still another $6 million to be made, and this is one of them. I think it may be believed that this is the hardest of them. I don't know. But the point is, why was Riemann interested in this? Because Riemann interested, this is called RH. RH implies ENT, which in his time was not a theorem. The Riemann hypothesis, he realized if you knew the Riemann hypothesis, the prime number theorem follows. That's one of the things Riemann realized. Okay. So, but it turns out the prime number theorem follows from something much easier. From what is here. So, Hadamard and Dalal Poussin in 19. Hadamard independently, the La Poussin, French guys. So, first one has to know how to pronounce their name, so we do it like this. Mar so this is always problematic, but you know, San is a bit tough. Okay. That's how you pronounce it. Yeah. So Harman, they prove that if you have the zeta 1 plus id is never 0. 50 is not equal to 50 is 0, of course it blows up, you know that already. But if you go anywhere else on this line, it's not 0. And it's a not very difficult proof, but I'm not going to do it here because you know an hour is up. And again, privately if you want to talk afterwards, that's not an issue. We can continue for those who want. Zeta 1 plus id not equal to 0 already does it. Okay? So that's relevant. And in fact, this relates to slightly more subtle question in general. So this was done in 1896. So almost, I think, about 70 or 80 years after Gauss conjectured the prime number theorem. But what can you say? So let's say a little more about the Riemann hypothesis. What the deal is, right? So first, what was special about 0 and 1? So one can say a little more. So it turns out the Riemann zeta function does attain the value 0, and it attains the value 0 at the points -2, -4, -6, -8, etc. Okay. Here are the zeros. These are called the trivial zeros. So here zeta of -6 is 0, for example. At zeta of -2n is 0. These are called the trivial zeros. So another way of saying the Riemann, formulating the Riemann hypothesis is all the non-trivial zeros. Okay. What did I do? Oh, I said something completely absurd. So this is yes, sir. I said go and you go up to half, but that's being recorded, so I should correct it. Okay, so you want to go all the way up to half. Yeah, sorry. Punchline got a bit messed up there, but okay. So it says all the non-trivial zeros lie on the line where s equals half. If there are zeros, they're going to lie here, nowhere else. That's the statement of the Riemann hypothesis. So, okay, what am I saying? Not equal to 0, and in fact, all zeros. So even stronger statement, zeta s equals 0 in this domain. I think that's what I really want to say. If this is what I want to say, let's make a precise statement. and theta s equals 0, then the real part real s equals 1 half. That's what I want to say. So if it is 0 in anywhere in the what's called the critical strip, then it must be on the line s equals half. So I'll spend 2 more minutes telling you why half is special. So okay, how does this relate? So again, right? So what's the moral of the story? You know more about the zeta function, and you've got much better information about the primes. It's not just that there are infinitely many primes, but they grow like Lix, or roughly like x by log x. That's the prime number theorem, and it follows from knowing that zeta 1 plus it is never 0. So on the line real s equals 1, if you know it's not 0, then the prime number theorem follows. The Euler product tells you it's not 0 up to here, but now you're saying, look, I know it on this line too, it's not 0. And Riemann said, look, if I go all the way there, it implies the prime number theorem. Of course, that's a much stronger statement. But Hadamard and Delavalli Pusa realized, look, you don't need to go all the way there, just show this much and you've already got the prime number theorem. So what does going all the way there get you? Okay, so that's the next. So it turns out, let's go here, that Riemann hypothesis, so we are not happy. Just because it's like Lix, we are still not happy. What does it mean? That's just an asymptotic statement, right? Pi x looks like Lix means they both, if you divide by Lix, you get limit goes to 1. But there could be some error term, right? So what this means is, so we know what the prime number theorem tells us is that pi x equals say Lix, right? And then plus something which goes to 0, which goes to infinity slower than Lix. That is, if I divide toward by Lix, then on the and take limit, this will be 1, and then this will be 1, and therefore this should go to 0. Right? So there's some error term. And the Riemann hypothesis says basically RH is equivalent to saying that E of x actually is O of, I'll explain this maybe, C times square root x times log x. So you see, this term grows slower than the main term, which is x by log x. But x by log x is very close to x. It's like almost like x, right? I'm saying the error term is much smaller. It's like square root of x. You've almost gained x to the half. This is what the Riemann hypothesis gets you. So far, it is unknown if E of x is even less than x to the 1 minus theta for any theta. So you can't even save a small power of x. We don't know how small the error term is. We only know that the error term is less than this. We have some partial information. One can write down something precise, but we know this much. Okay? So knowing the Riemann hypothesis is knowing the precise error term. So it's not just that pi x is x by log x. You know that the error term is not more than square root x. So that's what motivated Riemann. Last thing, why half? So Riemann proved much more. What's so special about the line half? Well, it turns out the Riemann zeta function satisfies the symmetry. And that symmetry is the following. So if I write Zs, or let's say psi of s, modify the zeta function slightly by the gamma function. This is the usual thing, integral 0 to infinity e to the minus x, x to the s, x by s, dx by x. And you look at this, it turns out that this is 1 minus s. In other words, if you take the value of this, what I call the completed zeta function, you have chuck in some gamma function, which doesn't really matter, then the value here is the same as the value here. And a simple application of what's called Schwarz principle actually says also the value here, because there is some symmetry around this real axis also. So the value here is the same as value here. So if you reflect in the line half, the value here is the same as the value here. So how did Riemann come up with the Riemann hypothesis? For a long time people didn't know, they thought he just guessed and so on. He did. I mean, obviously there is a guesswork. But sometime in the 20th century, Carl Ludwig Ziegel found some notes of Riemann. Ziegel is a famous mathematician from the last century. And he realized that Riemann had actually calculated it. So here is the thing. If you look at this function, on the line real s equals half, it's the real value. For all values of t. That means if you want to figure out if it takes the value 0 or not, you can look for sign changes.
Yeah.
And right, if it's positive here and negative there must have been a 0 in between. Right? So what Riemann actually did was he actually calculated this thing by hand. There are ways of doing it, right? And saw that there were sign changes. He calculated the first 3 zeros and realized that all of them seem to be on the line real equals half. Yeah. Nowadays, I think the record is 10 to the 14 zeros. The first 10 to the 14 zeros we know lie on the line real equals half. You can calculate it using computers, etc. So there's strong evidence towards it. Further, what is the other evidence? Hardy of Ramanujan fame claimed that, proved that, with Littlewood, proved that a positive proportion of the zeros lie on this line, real equals half. When it's go up to some height, there should be a certain number of zeros up to that height. In fact, T round T, as in fact, a positive proportion of them will lie on the line real equals half. That positive proportion is being strengthened to, I think 60% is the current record. 1/8 was proved by Selberg, then Levinson did 33%, and right now I think they're at around 59 point something percent.
Where does the other?
Sorry?
Where do the other roots lie?
No. We want to say 100% of them lie there, but we are only able to say 59% lie there at this point.
Okay.
Yeah. So because of this functional equation, the line S equals half is special in some sense, and I'm saying that all the zeros lie there. Those of you who have heard of the argument principle or Rouché's theorem in complex analysis know that by going in a contour like this, you can count the zeros of a function, complex function. So on the one hand, numerically, you can calculate this contour integral and you know how many zeros there are in some box. On the other hand, you see how many sign changes there are in the box. If these two match, you know you've got all the zeros that there are in the box. So in this way, you look at a box of height t, and you can go, as I said, you can prove that the first 10 to the 14, whatever, zeros are actually there. So you have lots of numerical evidence of the Riemann hypothesis, but 10 to the 14 is not infinity. There could always be some zero that's outside that. Yeah. So that's what the Riemann hypothesis is. The Riemann hypothesis is equivalent to giving a very precise error term for the prime number theory. Part of the motivation for it. Okay. The general philosophy, why do you take 1 over n to the s? That is a philosophy. More generally, if you have any sequence of numbers with some number theoretic meaning, ans, right? Some of you may have seen this idea that you use a generating function, right? You look at summation a n x to the n, you get a power series. Why do you do that? Because then the tools of algebra and analysis come into play. You now have a function and you can differentiate it, you can do various things that satisfy various relations. Relations that the function satisfy get reflected in the properties of the ans. You may have seen this with Fibonacci or something, right? Here, you bring the tools of complex analysis to bear. You have an n to the s. Complex analysis is even better than real analysis. If a function is differentiable once in complex analysis, it's automatically infinitely differentiable and has a power series. So complex analysis, if a function has a derivative in the sense of complex analysis, it's an extraordinarily good function. And therefore, you have the tools of complex analysis you can use to bring to bear on the problem. Which is one reason you introduce some function like this. As you see, it came sort of naturally through Euler, etc. And what is the guiding principle? Good properties of this function should reflect some properties of the sequence that you're looking at. This particular sequence happens to be related to prime numbers through the Euler problem. Yeah. And okay, so as a small side note, when Srinivasa Ramanujan wrote to Hardy, initially he wrote letters to Hardy in Cambridge. All of you are probably familiar with that story. He claimed a very precise error term in the prime number theory. He said, I have a wonderful formula or something. Yeah. And that's one of the things that got Hardy interested in the letter, in Ramanujan. And then he brought him over to Cambridge and etc. Right? The rest is history. But ironically, that claim of Ramanujan was wrong. So he had made a mistake. But in any event, so Ramanujan had amazing intuition, but he didn't know any complex analysis. So he actually thought that the data function had no zeros except these. And Hardy writes somewhere, on the one hand you don't want to destroy Ramanujan's confidence by telling him he's wrong all the time. On the other hand, he said you can't let him go through life thinking all the zeros of the data function are here. Whereas in fact almost all of them are here. This is a sparse set and there are many more in this tree. So it's impossible to let him go through life thinking that all the zeros of the Riemann zeta function are trivial. So that's some connection. Ramanujan also wrote down the following formula. Perhaps some of you have heard that this is equal to -1 over 12. Some of you must have seen this.
Yeah.
What does this mean? Now you know what this means. This is data of -1. if you were to think of it formally, there's nothing but zeta of minus 1, right? But now we have given zeta of minus 1 a meaning. We know how to give it meaning. We gave it a meaning, and what Ramanujan really meant when he wrote this down, well, he didn't know, but this is what he really had in mind was, or no, he didn't have in mind, what we have in mind after the fact, knowing what Ramanujan did, is that zeta of minus 1 is minus 1 over 2. That makes perfect sense. Zeta minus 1 makes sense, but the series does not. And this is part of the general principle of analytic continuation, that you find some other formula that makes sense. It coincides with the original formula wherever that original formula was defined, but now we have a new way of studying the function outside the original domain of definition. And the good news is there's only one way of, if you can do it, there's only one way of doing it. So I'll stop it. There's lots more to say, but I'll stop. Questions? Fortunately, it was corrected in time before. Yes.
So,
No, let me. I'll come in.
how do you write down the statement that zeta of s not equal to 0 if zeta of s is greater than 1?
That is follows from the Euler product. That's a product, right? Now, product cannot be 0 unless one of the terms is 0. General fact, right? In an infinite product, it cannot be 0 unless one of the terms is 0, but it's 1 minus 1 over, that's never 0 over next 0.
Does that still apply to formal terms?
Yes. Everything that you know about resonances will carry over. Still applies for complex numbers.
Sir,
Being non-zero is being non-zero, whether it's real or not.
sir, the distribution of primes,
Sorry?
the distribution of primes and like the structure that we see, the similar structure do we see in any other context?
Any other what?
Any other context like physics or any other domain of maths or
No, I didn't answer. Do we see any other?
in any other context?
The prime number.
No, like in general, the distribution or the density or the gap or anything that links it.
See, distributions in other places, of course.
Like primes.
Okay, let me make some fancy statement, which perhaps neither I nor you may understand at the end of it. Yeah. Huh? One answer, yeah.
Guys, before you leave, we have snacks outside. So it's like just in case they want, you can help them.
Much better than what I'm going to say. Which is, no, see, here's the point. So, for example, one way of thinking about the Riemann hypothesis is via physics, where the zeros of the Riemann zeta function are supposed to correspond to the eigenvalues of the Hamiltonian of some physical system. It's a fancy and popular way of approaching the problem since for the last 40 or 50 years, which has got nowhere. Yeah.
So if like the function is symmetrical about the line where the real part of it
Yeah.
S is half,
Yeah.
then that would mean there are other zeros on the real where the
No, the completed function. See, the point is this gamma function becomes infinite exactly as the negative real integers. Yeah? But we know that the product makes sense, and that happens because zeta becomes 0 at the negative integer. So it's not the zeta function, it's this psi function. Oh, I wrote, oh god. Terrible. No, this is psi. I started writing, it's the same function on both sides, otherwise of course it's I started writing z and I forgot to see. Sorry, take this as question.
Yeah, so I think I follow how you claim that using my you can say that the error term follows that.
No, I have not proved this. It was a derivation. The last 15 minutes of the talk were essentially statements unsupported by or arguments.
Sir.
Yes.
You mentioned that those minus 2, minus 4, minus 6 are trivial zeros. How
Yeah.
trivial is it to prove they are zeros?
Oh, it's very easy because it's easy to see that this product makes sense, and it's very easy to check that the gamma function has a pole, as they say, it becomes infinite at -2, -4, etc. Right?
Yes.
That's easy because
Yeah.
you have gamma s plus 1, it's s gamma s,
yeah.
right? And now using, by the way, this is kind of, the way we get the analytic continuation, the way we extend the zeta function to the whole plane is similar to this. Gamma s makes sense for real s greater than 0, right? When you define the integral. But then using this formula, it makes sense for real s greater than -1, because gamma s is also gamma s plus 1 by s. Now gamma s plus 1 makes sense for real is greater than minus 1. The integral will be equal to 1 when real is greater than minus 1. So now you have a new definition of gamma s which extends to minus 1. Repeat, you go to minus 2, etc. Right? So in some sense what we are doing, the zeta function is exactly the same thing. You're moving to the left in W.
Sir, is eta function a complete function?
Sorry?
Is eta function, this bigger function,
Psi.
okay.
Yeah.
Is that a complete function? Is that a probability like
Yes,
better function?
no, we like psi because even better behavior than zeta in some sense.
Okay.
So of psi of s, so the fact is, in fact, you can do better. S times 1 minus s in psi of s has no bad behavior at all. It's defined everywhere. Psi of s itself may have bad behavior. It has bad behavior at 0 and 1. And it has a pole. It has a pole of order 1 with residue 1 and minus 1 and 0. But if you take psi, it is nice. Psi is nice because it's symmetric in s and 1 minus s completely.
What are the implications of the error function here?
What are the errors? Okay. None, it's just that other than except in the sense that you want to study how many primes there are to x and you would like to know that you are not off by too much. Your first guess is roughly x by log x. Now you don't want to have a huge error. So if you are able to get it down to x to the half, you are happy. You have saved a whole half from. Okay. Riemann hypothesis does imply a huge number of other statements in numbers here. I can't get into them at this point. But there are, Riemann hypothesis has tremendous implications. So very often people will prove theorems now, assuming the Riemann hypothesis. That has, you do it for two reasons. One is, well, you like to still, everybody believes the Riemann hypothesis is true, so you still like to know at least that your other statement is true. But also very often, once you prove it using the Riemann hypothesis, somebody will, or the same person may find a way of proving it without. Once you get the idea of the structure of proof, you realize, oh, I don't need something so strong at this point. I can substitute it with something weaker than its own and get a proof without an unconditional. The third reason is, maybe you'll get a contradiction and prove the Riemann hypothesis false. That we don't expect. So numerical evidence for Riemann hypothesis is quite strong. First 10 to the 14 zeros, but also better, roughly 60% of all zeros are also known.
Why do they estimate the number of zeros and they don't know how many?
No, you know that I didn't say that in a box of height t, you go up to imaginary part capital T, then there are t of t. There are t of t by 2 pi 0. That just follows from the argument to this. When you do integral fz by f prime z dz and you go around, that counts as zeros and poles. So that argument is very easy, that t of t by 2 pi.
Then also how you use this fact that the real line of psi half is actually always here, which means that psi of half is always here.
Psi of half is here, that allows you to count zeros in another way using Sanchi. So you're counting zeros in two ways. One is with the so-called argument principle using control integration complex answers. The other is simple Sanchi.
That is the control that there is no other zero apart from the one that you get.
That's right. So you count everything. There are this many in the box, and you can calculate that to incredible accuracy because it's a contour integral.
Yes.
Numerically, you calculate it to great accuracy, and you know it has to be an integer.
Yes.
So if your answer is for the contour integral is 27.222, and you know the error is not too big, you know the answer is 27. Right? So you can calculate that to great. In fact, that's what Riemann did it. So he actually calculated the first three, and I think what are the first three zeros had imaginary part. What were they? I think I noted them somewhere. No, I don't have it noted down, but I think the third zero comes with imaginary part roughly 27. So he calculated the first three, he made some notes, and people don't know, maybe he just guessed. No, he actually calculated. High degree accuracy. Yeah, those guys were fantastic, phenomenal. They could calculate the hell out of it.
So with that -2, -4, are there any zeros?
Sorry?
Are there -2, -4, -6, etc.?
Ah.
Are there any zeros where real part less than 0?
Are there any zeros?
Where real part less than 0?
No, those are the only at -2n. you have zeros and you don't have any other zeros.
That has been proved.
That's easy because then you have this function equation. So anyway, it is non-zero here, and then you reflect here, and the only problem comes wherever this blows up. So if this doesn't blow up, I won't have a zero because etc. So you can use the function equation. It's straightforward, not a hard thing. So those are the only zeros. They call it trivial zeros. Only other zeros, and all the other the important ones lie on the line realistically.
Sir,
Yeah.
sir, do you know for certain that the non-trivial zeros are infinite?
Infinite.
Yeah, in number.
Yes, they are. If you go up to height t in this step, capital T, then there are roughly t log t divided by 2 pi 0.
And that has been proven, right?
Yeah, that's a simple complex analysis. If you have seen what's called the argument principle, if you have any nice complex function, then by taking a contour integral around this box, you can just calculate integral fz by fz, integral fz dz by fz, will count the zeros. So you can do it and it's t log t.
Sir,
Yes.
it's not outside now, so I think we can take a break and have more discussion over a cup of tea.
Okay.
Are you the presentation?
Oh, nice.